All right, welcome back. We're going to go through some abnormal examples of integration by parts. These are called test-style questions. Generally speaking, when you're given an integral, you're not told what to do with it. You just have, here's the integral, figure it out. Figure out what method you're supposed to use, and that's often the hardest part. And these following examples, that step of figuring out what to do is not asked of you. You're told what to do, and you just have to follow through. So in this example, integral from 0 to pi over 4 of x times secant squared of x, we're asked to use integration by parts with u equals x and dv is equal to secant squared, and identify which of these expressions is equivalent to that. So it's taking away the component of the problem where you have to choose the strategy and just focusing on the execution of the strategy, and only the first step of that execution. So I'll write that down. Generally, we are not given the strategy. In the next problems, however, the strategy is given. So you have to follow it. Just do what's asked of you. So I'm going to identify that this integral can be rewritten as uv, evaluated from 0 to pi over 4, minus the integral from 0 to pi over 4 of v du. We're going to have to find out what u, v, and du are. So using the LATE acronym, L-A-T-E, we don't have any logs. We do, however, have an algebraic term. We have an x, so I'm going to let u, oh, never mind, like I'm on autopilot. It's telling me to let u equal x. So if u is equal to x, then du by dx is equal to 1. So du is equal to dx. Right, we were told, we're not using LATE, we're just told to do it this way. So I have an x there, I have a dx here. And then we're told that dv is equal to secant squared of x dx. Well, we're going to do what we always do, we're going to integrate it. V is the integral of secant squared of x dx. So what do we take the derivative of to get secant squared? And the answer is tan of x. So I have x times the tan of x, evaluated from 0 to pi over 4, minus integral of tan of x, integrated from 0 to pi over 4. Okay, then we can simplify. Let's plug in the top bound. So pi over 4, so I need more space, I'll do that over here. Pi over 4 times the tan of pi over 4, when we plug in the top bound, minus 0 times the tan of 0 when I plug in the bottom bound. And then the last part, yes, we can integrate that, but look at the options. None of those options are telling us to complete that integral. We're just asked, do integration by parts once and don't do anything else. All right. Next piece, what's tan of pi over 4? Tan of pi over 4 is 1. Tan of 0 is 0, but it's multiplied by 0, so it's like doubly 0. And we can look at those options. I have pi over 4 minus the integral from 0 to pi over 4 of tan of x. So that is option A. That's it. Okay, similar type of question. we're told to apply a particular u and dv to an integral. Apply this set of choices to the integral from 0 to 1 of e to the x. I'm going to correct this. I'm not going to go from 0 to 1. So allow me this fix to make this a more reasonable question. I'm going to go from 1 to 2 because I don't want to have a improper integral. E to the x over x is undefined at 0. So we have a small problem if we're going from 0 to 1. Well, more than a small problem, it's a massive problem. So if we fix it, we change the integral from 1 to 2, it's okay. And I'm not like using secret math to say that this is equal to what was there before. I'm just changing the question so it's properly defined. Didn't even notice when I wrote it. All right, so anyways, we're going to use this set of transformations, if you want to call them that, even though it's a very different process than transforming using substitution. We use this instruction to rewrite the integral. So we recognize that this is going to be written as uv integrated from 1 to 2 minus the integral of v du integrated from 1 to 2. If u is equal to x, when I take the derivative du by dx, or e to the x, derivative of e to the x is e to the x. I'm going to rearrange du is equal to e to the x dx. So that part's done. Then dv, we're told, is 1 over x dx. I'm going to integrate both sides. To get v, and we find v is equal to ln absolute value of x. So we'll take that, we'll take our e to the x dx thing, and we'll plug both of those into our integration by parts formula. So we have u, which we said was we were told was e to the x, times v, which was ln absolute value of x, minus the integral from, and this is evaluated from 1 to 2, minus the integral from 1 to 2 of v, which we found was ln absolute value of x, times du, which is e to the x dx. Okay, and I'm going to plug in 2. We have e to the 2 ln 2. And plug in 1 minus e to the 1 ln 1 minus the integral from 1 to 2. I'm going to put the e to the x in front of the log function. It's a little bit more standard to do that. I'm going to drop the absolute value symbols because we are integrating from 1 to 2, which means we're integrating over positive numbers. So we don't need absolute values. If x is positive over our region of integration, the absolute value function, or absolute value sign can be dropped. Or left. It's not wrong to leave it. Ln of 1 is 0, so that second piece is going to disappear. And then just get rid of the e times 0, it's just 0. That's our answer. So we didn't fully solve because we weren't asked to fully solve. We were asked to use integration by parts once and see what we get. If you're curious, I wish about that last integral, the integral of e to the x times ln of x, and you want to try it, I wish you luck. And I wish you not to waste too much time trying to. All right, next example. Same format. It's a weird question. We're asked to transform the integral from 1 to e of ln of x over x using integration by parts, to rewrite it, Can we reformulate it into a nicer integral? And maybe these instructions are not going to lead to a nice expression. Maybe it's going to make it worse. But we're just going to follow the instruction. So this integral of what we're calling uv, or udv, we're going to write it as u times v, evaluated from 1 to e, minus the integral of v du, also evaluated from 1 to e. We need to find the pieces to plug in. I'll take the derivative of u, du by dx is 1 over x. So du is 1 over x dx. V or dv rather is 1 over x dx. V is the integral of 1 over x dx, which is ln absolute value of x. So we'll plug those pieces in. So we have u, which is ln of x, times v, and v we found was ln of x, or ln absolute value of x. Might as well maintain the absolute values, not that they're going to matter, because we're going from 1 to e, and 1 and e are both positive numbers. We're not spanning over any of the negative x values. Minus the integral from 1 to e of v du. So v is ln of absolute value of x, du is 1 over x dx. Now we can plug in, let's see, u is ln x, v, got that. Okay, so I'm going to plug in e, ln of e times ln absolute value of e, which is just ln of e, minus ln of 1 times ln of 1, minus the integral from 1 to e of ln absolute value of x, which can just be rewritten as ln without the absolute value of x, and then multiplying by 1 over x is the same as dividing by x. Again, I'm dropping the absolute value signs because our integral is going over positive x values only. It's not wrong to leave the absolutes in there. Okay, ln of e is 1. So 1 times 1. Ln of 1 is 0. So 0 times 0. So we get 1 minus integral from 1 to e of ln of x over x. That's our answer. Now think about what this is telling us. We're done the question. We were done what we were asked to do, but look at what we have. We have something marvelous. If you're trying to solve this problem, we've basically done it. We have an integral from 1 to e of ln of x over x dx is equal to 1 minus itself. Well, I'm going to add that integral to both sides. I'm just going to rearrange. So it's like I have a is equal to 1 minus a. So 2a is equal to 1, and that means a is equal to 1/2. So that means the integral from 1 to e of ln of x over x dx is 1/2. And what's beautiful about this is that we didn't finish integrating any expression. The only integral we did was the integral of dv. The rest of it was just playing with the integration by parts formula and doing some final rearranging at the end. So it was a very elegant way to solve the problem. This problem can also be solved using substitution. But I think not in as elegant of a way as this. One more problem, one more test style problem. We were given sorry, I had to pause for a second. We're given a similar structure. We have an integral from 1 to 2 of a function 3x squared plus 2x times e to the x squared. And we're given the instruction to, oh, I have a typo here. Tisk tisk. I changed my numbers in one spot and I didn't change them in the other spot. So I'll change them right now. These should be 6s to match up. Oh, lots of stuff has to change. My goodness. It should match. I changed it and must have got distracted. Okay, so we have the integral from 1 to 2 of 6x squared minus 6x times e to the x squared dx. And we're going to transform this using integration by parts with u equals e to the x squared and dv is equal to 6x squared minus 6x times dx. Okay, so we identify that this is going to be equal to uv evaluated from 1 to 2 minus the integral from 1 to 2 of 6x squared minus 6x. Oh, what am I doing? V du. Okay, so we have to find the pieces. I'm going to take the derivative of u, so du by dx. To take the derivative of e to the x squared, I have to use the chain rule, e to the w times w prime. So du by dx is e to the x squared times 2x. Rearrange, just multiply by dx on both sides, so we get 2x e to the x squared times dx. So that's going to replace the du inside our integration by parts formula. Now I'm going to do the same thing we always do for v. To get v, we have to integrate dv. Each part can be integrated using the Antipower Rule. We have 6 times 1/3 x to the power of 3, so it'll be 2x cubed. And we have 6 times 1/2 x squared, so it'll be 3x squared. That'll be our v. So we'll plug that in for the v. So u was e to the x all to the 2. V 2x squared minus 3x, 2x cubed minus 3x squared. And then that's evaluated from 1 to 2. Minus integral from 1 to 2. V is that thing in green that we just found. And then du is 2x e to the x squared dx. Now we can simplify the first part by plugging in the top bound and the bottom bound and evaluating. We get e to the 4 times 16 minus 12. Plug in the bottom bound. E to the 1 times 2 minus 3. And in the last part, I'm going to multiply the 2x into the green brackets. I have a 2x times a 2x cubed. That'll be a 4x to the power 4. Minus 2x times 3x squared. We'll have a 6x cubed. E to the x squared dx. And then we can just simplify the numerics inside. We have 16 minus 12, so 4 e to the 4. We have 2 minus 3, so negative 1. There's already a negative in front, so it becomes positive e. And now we have minus integral 4x to the power 4 minus 6x cubed times e to the x squared dx. So this is worse, but that's what we were told to do. We made it worse. Made it worse, but We did what was told. We attempted to use integration by parts to simplify this integral and found a different integral. Oh, missing something, missing the bounds from 1 to 2. 1 to 2, 1 to 2. Found that it's equivalent to this, and this is way worse. We raised the powers of x. So you may be thinking, well, why don't we flip it? Why don't we let u equal to 6x squared minus 6x, and then we let dv equal e to the x squared? The reason we don't do that is if dv is equal to e to the x squared, to get v we need to integrate e to the x squared. And that is something we can't do. So integration by parts is not the way to solve this problem. I'll stop here. That's, oh, I'm a liar. There's one more. I forgot I added one more example. I thought there weren't enough of these just to cover all the bases. Make sure all the pieces match this time. Yeah, okay, all the pieces match. We have an integral from 1 to 2, and that's safe because it doesn't include 1/2, where the bottom of their integrand is 0, of 12 times cos of pi x over 1 minus 2x, and we're going to use integration by parts formula to rewrite the expression. And this one's also a better phrasing of how you would see a problem on a test, but do not attempt to complete the integration of the resulting expression. So stop whatever you have, whatever horrible thing you've created, don't go any further. Because what's going to come out of this is likely not better than what you start with. But we'll do it anyway, because that's what we're asked to do. So if we're using integration by parts, then this expression is going to be uv from 1 to 2 minus integral of v du from 1 to 2. We're going to have to take derivatives of stuff and antiderivatives of stuff to get our pieces. When we take the derivative of 12 times the cos of x, we'll have 12 times negative sine of w times w prime. We have to use the chain rule, where w is equal to pi times x. So w prime is equal to pi. So a negative 12 sine of pi x times pi. And we should put that pi with the negative 12. So negative 12 pi sine of pi x. So that means du is equal to that times dx. Plug that in for the du term. We also will need v. So we start with dv 1 over 1 minus 2x dx. And this is a tougher one to do. How do we integrate this? I'm going to use substitution. Sub with w is equal to 1 minus 2x. So I guess I should do the integral part too. So we have an integral of 1 over w, but we have to replace the dx to do a usual thing. So I'm going to take the derivative of the substitution, dw by dx, 0 minus 2. So dw is equal to negative 2 times dx. But remember, with substitution, we have to isolate for dx. So I'm going to divide both sides by negative 2, negative dw over 2, and just bring the negative sign up. So we can bring the negative 1/2 in front of the integral, antiderivative of 1 over w dw, which is negative 1/2 ln absolute value of w. We get a plus c, but we have, number one, we have bounds, and number two, we never include the plus c at this stage of integration by parts. The last thing we have to do is undo the substitution. So negative 1/2 times ln absolute value of 1 minus 2x. And then that's going to get plugged in up above. Okay, so u is 12 times the cos of pi x. V is that green thing we just found, minus 1/2 ln absolute value of 1 minus 2x. And we have an integral from 1 to 2 of v, which is the green thing again, negative 1/2 ln absolute value of 1 minus 2x. Multiplied by the du, the thing in blue, minus 12 pi sine of pi x dx. So negative 6 cos of pi x times the ln absolute value of 1 minus 2x. Evaluated, I forgot to evaluate that from 1 to 2, minus, so we have three negatives there, negative times negative 1/2 times negative 12, the three negatives will end up with a negative. We can multiply the constants together, we have a 6, bring that out front, integral from 1 to 2, and then might as well put the pi out front with the 6, so minus 6 pi, integral from 1 to 2 of sine of pi x times the ln of 1 minus 2x, absolute value, dx. Plug in the top bound. So negative 6 times the cos of 2 pi times the ln of absolute value of 1 minus 4, so absolute value of negative 3. Plug in the bottom bound, negative plus 6 times the cos of pi times the ln of negative 1, absolute value, minus 6 pi. I'm just going to rewrite that second line. No change happens there, we're not supposed to integrate it. Cos of 2 pi is 1. Cos of pi is negative 1. So I'm going to get negative 6 times the ln of 3 plus 6 times negative 1 times 0 minus 6 pi integral from 1 to 2 of sine of pi x ln absolute value of 1 minus 2x dx. I ran out of space, but the only thing I would do in the next line is I'd get rid of that 0 piece. Get rid of that second piece because it's not contributing to it. I have one more correction to make. This ain't test style, this is too hard. This is too much to put as a test question or an exam question. It's the stuff of nightmares, actually. My intention was not to make something this brutal. So don't worry, like when you look at an example like this, if you see anything like this in the homework, if you see anything like this in any of the materials, and you're worried about it appearing, just ask, and I'll tell you. Like this is way too much. But the other ones, this one was okay. This one was good. This was the right difficulty, and this one's probably the best of the examples. Fairly clean, and this one too. See you next time.